All right, so what we're going to do is we're going to take a look at examining what is a Taylor polynomial. And the first thing we want to identify is trying to discover what a polynomial or what a Taylor polynomial is and what it's going to be used for. And so we're going to work at this incrementally and start with this function right here. So if we look at this function right here, we might say that the graph of this is a line, and the equation of that line would be y equals x. That would be true in most situations. However, what we need to think about in calculus is this concept of local linearity. And so if you zoom out of this graph a little bit, what you see is actually this graph right here. And this box is what we actually zoomed in on the first graph. And so locally, this part of the graph does mimic the equation y equals x. It is very close to being a linear function. And so if you zoom out and we think of this could be a cubic graph. Initially, let me change the setting a little bit here so we can see the whole paragraph. Initially, we were looking at the part of the graph in the box, and at that small scale, it did appear that the graph was a line. In this larger view, you see that it's actually the graph of a cubic polynomial. Or is it? It could be some other kind of graph that behaves in this manner. All right, so let's go a little bit further with this. If you zoom out some more of that original graph, again, this box shows that viewing window that we had a second ago. And so this gives you a little bit better idea of what that graph actually was. Okay. Now, as we can see, y equals x does approximate, and that's the blue line right here, it does approximate the sine function near the origin. And at the origin, it actually is a perfect approximation because if x is 0, you get y equals 0. And at x equals 0, the sine of x is also equal to 0. We can see that the approximation breaks down, however, as you move away from x equals 0. So as you move away from x equals 0, what happens is your blue line starts to deviate away from the sine of x graph. And the further away you get from 0, the further it's going to deviate. So the graph above suggests that there might be a cubic function that does a better job of modeling the sine function on a wider interval. So what if we can come up with a cubic function that hugs this curve for a longer period of time than this line does? So right around x equals 0, we have a real good approximation for the sine function using this line. However, the further we get away from that 0, the more error we're going to have involved with this. So what we want is we want a function that's going to hug this curve for a little bit longer. And so let's try using a cubic function to help model this. Well, we already know that the sine of x is approximately equal to x for small values of x, simply meaning that that line was a pretty good approximation as long as x was close to 0 here. So let's hang on to that and tack on a cubic term. So we're just going to add a cubic term to this. And the cubic term will be in the form negative kx cubed to get this equation. Now it's negative k because we want to think about end behavior. To the left, we need our graph to go up because our sine function is going to go up to the left and down to the right. So up to the left and down to the right means that our cubic function needs to be a negative cubic function. All right, so if we remember this right here, this cubic, it starts bending too soon. We need it to hug this sine curve for a longer period of time. See right here, this line is actually a better approximation. So we need this curve to hang on to the sine function for a little bit longer. The graph shows that y equals x minus x cubed is not particularly good because it is too cubic. The bend in the curve starts a little bit too soon. All right, so the way that we can fix that is we need to reduce the influence of the cubic term. And we can reduce the influence by using a coefficient that's closer to 0. All right, so we're going to try 1/10 to give us this equation. All right, so for this graph, we can see that we overdid it a little bit. All right, so x minus 1/10 x cubed, that's going to be this green graph here. And you can see that it did hang with the sine curve a little bit better than the original one, but it overshoots the sine curve. Okay, the sine curve is down here. So that means we reduced this by a little too much. Okay. All right, so let's try y equals x minus 1/6 x cubed. All right, so when we do that, we get this curve right here. So you can see that the green curve, it hangs with this sine function, which is the red one, hangs with it a lot longer. Okay, and it is a better approximation than this line was, okay, because it is very close to that sine curve for a much longer period of time. You can see right here the error between this point. Let's say you pick a point here, an x value here. On the cubic function, it's there. On the sine function, it's right there. It's real close. And on the linear function, the value would be way up here. So this cubic graph here is going to be a pretty good approximation up to a certain point. Now, once we start getting further away, you can see that that error, the difference between, which is your difference between the sine function and the polynomial, that error starts to increase the further out we get. Now these, graphically, this function does a better job of approximating sine graph on a larger scale than the linear graph did. And you can see some of these actual values for the sine of x and the polynomial x minus 1/6 x cubed. So when x is 0, it's a perfect approximation. As we move away from x equals 0 to the right, well, we're still pretty good approximation here. It's the same up to 4 decimal places. Here, it's off by just a little bit, about 1/100th of a point. Here, it's off by a little bit once again. Over here, it's off by a little bit. And even here, even all the way out to 1.2, you see it's not really that far off. It's 2/100ths of a decimal off. And so it's going to be pretty good approximation even out to 1.2. Could we do an even better approximation? That's the question. Could we get a better approximation out of a polynomial that will mimic the sine graph for even a longer period of time? See, on the cubic term, the deviation started right here, which was before the hump for the sine curve, or where the maximum value was. So, okay. All right, so if we start with what we could, if we start with what we have, we could add on a quintic term, which is going to be your x to the fifth power. All right. If you play around with the quintile term a little bit, you can try this one right here, 1 over 120 x to the fifth. And that is going to be the green curve, and you can see that it does stay pretty close to the sine graph for a little bit longer period of time. It really doesn't start to deviate until you get about to about right here. That's when it starts to branch off from the sine curve. And as you can see, that is about where the hump starts to come down, a little bit past that. All right, so as you can see, this approximation is getting closer and closer to the sine curve. Is there any reason why we should stop at 3 terms? If we continue this process with more terms, could we get a reasonable approximation of a sine curve? Well, here what we have is going to be a 7th degree polynomial. And as you can see, the 7th degree polynomial, which is the green curve, it stays pretty close to the sine curve for one full cycle of that sine curve. So for one full cycle, it is a pretty darn close approximation of the sine curve. So let's try 9th degree. Well, 9th degree polynomial, it hangs on even further. It goes a little bit even past that one cycle. Well, how about if we go to the 11th degree and the 13th degree, and even further out to the 15th degree. The 15th degree now is a pretty good approximation for 2 entire cycles of that sine graph. Well, if you notice the pattern of our polynomial, we have x minus 1 over 3 factorial x cubed plus 1 over 5 factorial x to the fifth. And that just continues on. You can see your denominators are going up by odd values. And then the exponents are also going up by odd values. This leads us to a generalized equation of a polynomial that will approximate the equation y equals sine of x. So y equals sine of x is approximately equal to this polynomial. Now, the negative 1 raised to the n power, what this part of the problem does is it alternates your signs. As you can see from up here, we're going from a positive to a negative to a positive to a negative to a positive to a negative. This is an alternating sequence here, or series. And so to make your signs alternate, we have negative 1 raised to the n power, where if n is 1, this will be a negative value. When n is 2, this is a positive value. 3, this is going to be negative again, and so on. So this alternates your signs for the series here. Now, think about your exponent 2n plus 1. To make any number guaranteed to be even, if you want to turn any number into an even number, all you have to do is multiply it by 2. That will turn any number into an even number, just multiplying it by 2. And then if you add 1 to that even number, that guarantees you to get an odd number. So 2n plus 1 will always give you an odd number. So when n is 0, that gives you x to the first power, which is just x. And then you'd have 1 factorial in the denominator. And that gives you your first term up here. When x is 1, you're going to get 2 times 1 plus 1, which is x to the third. That's this x to the third here. And then you get 2 times 1 plus 1, which is 3 factorial. And that's the 3 factorial that we see here. And then when n is 1 here, this is going to be a negative value, which we have a negative in front of that term. Okay. Back here is that this is a Taylor polynomial, okay, because there is a definite ending point. We're saying, for example, up here we went to a 15th degree. Well, 15th degree means our n value was 7. So this was basically a partial sum. Now, if we were to continue this forever, and we were to put, for example, a ... on this, and continued this on forever, that would turn this into what is called a Taylor series. A Taylor series continues on forever. And if we were to continue this on forever, you also got to remember that when we went to 15th degree, it modeled it pretty darn close. And if you continue that out forever, it actually is going to be the sine function. Now, the polynomials that we have been developing and graphing, these are called Taylor polynomials, after the English mathematician Brooke Taylor. Every Taylor polynomial has a center, which in the case of our example that we just did was x equals 0. When a Taylor polynomial is centered or expanded about x equals 0, we sometimes call this a Maclaurin polynomial, after the Scottish mathematician Colin Maclaurin. Now, a Maclaurin polynomial is just a special type of Taylor polynomial. A Taylor polynomial applies to the whole thing, and then this applies to all kinds of polynomials. They could be centered at x equals 0 or centered anywhere. Maclaurin polynomials are only centered at x equals 0. Okay. Using this vocabulary, we could say that p sub 5 of x is equal to this. The 5 here indicates the degree of the polynomial. So this polynomial is the 5th degree Taylor polynomial centered at x equals 0, all right, for the sine function. Alternately, we could call this the 5th degree Maclaurin polynomial for the sine function. And we can call it the Maclaurin polynomial because it is centered at x equals 0. One thing I want to mention, so what are some observations that we can make about Taylor polynomials? Well, their accuracy at the center is perfect. Okay, so the functions match exactly or perfectly at the center of polynomial. Remember, that center is what we expanded from. Okay, and so we started with a sine curve, and then that sine curve was like this, and we said, okay, well, if we start at this point, we're going to get a perfect match, and as we move away from that, then it starts branching off. Okay, so At the center, it was a perfect match. The accuracy as you move away from the center, well, it's going to lose accuracy as you move away from the center. However, if you add more terms to your polynomial, then you are going to gain more accuracy. Once again, remember that we went up to a 15th degree polynomial, and it modeled that sine function pretty well for those 15, or for 2 cycles rather. Okay. Now, the